This is a version of the grapher that we've been using in the course that has sort of a nice feature for exploring how shapes of graphs change when numbers that are specified as parameters in a formula are allowed to change. For example, the default thing that comes up is ax squared plus bx plus c as a function, the one in red. So if I graph that, what's going to show is the blue thing, the g of x, graphed with the parameters a, b, and c set to constant values so that I get a graph, a thing that I can graph, and sliders so that you can move the slider and change the parameters. Watch what happens when I move slider A. A is the coefficient of x squared. It's currently 1. Let's move it somewhere else. And you see how that changes the shape of the curve. And you can similarly move B. C is the constant term. You should expect that to correspond to a vertical shift, and sure enough it does. So that's the way that the parameters look. Now, what I want to do is to use this to explore what happens for the situation where we had damped harmonic motion. Remember that ugly equation that we had? I was hoping this would work to let you just copy and paste, but I'm not sure that will work. You might be stuck with typing this in, but you could do that. I'm going to move it off screen so I can get the focus back and type. So I'm going to type it in exactly as it was. It was A times exp, that's the exponential function, of minus b times x over 2m. B is the damping factor, so what's happening, you'll see what effect that has. What that does is it makes the motion go to 0. This is times this is the part where the harmonic motion comes in, cosine of square root of c squared minus b squared divided by a term that also has the mass in it, 4 times m squared times x. Okay, so it's an ugly formula, sorry about that, but what it has in it are pieces that correspond to parameters that say what the shape of the thing is going to look like. So let's graph it and see what we get. Notice also the formula in the book doesn't use a C, it uses a W, but the way I set this up with the parameters, I have sort of generic A, B, C, D, and M, so I had to use C as the parameter to get a slider to work with. So here's the graph. And sure enough, watch this thing. You're watching the motion of this over time, and it's going up and down, but then it decays away. Let's make B 0. If the damping factor is 0, then it doesn't decay away. So I'm going to move B to 0, and that has the purely harmonic motion we're used to seeing. Let's go back to a bigger value of B and make the decay steeper. Now let's try some other things to see how they vary. C is going to affect the period of this thing, so we make C bigger and it makes the thing squeeze in, so there's more oscillations per unit time. A affects the amplitude. We can make the thing grow or shrink. If A is 0, it's just a flat function, 0. Negative A, so it starts out below. And M has the effect of how how much it oscillates. So look at this. Negative M, and it's unstable. The oscillations are growing as time goes forward. So if it's worth it to enter this and play with it, and if you like this application, it would be fun to use it for some other classes of functions that you might try as well. Anytime you could let parameters vary, you might be surprised at how that affects the shape of the curve.